So let's look at question number 6. In question number 6, we are looking for a decrease in the amount of NO. NO is here. Now if we're looking to decrease this, that means that we are looking to have our seesaw go in this direction. Because in addition to having the seesaw tell us the direction of the equilibrium shift, it shifts towards the upside. But it also tells us what occurs with the concentration. So if something is on the lower part of the seesaw, its concentration goes down. And if something is on the upper part of the seesaw, its concentration goes up. Just the direction that the seesaw falls. So here we're looking for a change that's going to cause the seesaw to shift down. Now the first item listed is a decrease in pressure. Now pressure only affects gases, and pressure only affects gases that have different number of moles on the reactant side as product side. Here we can see, based on the coefficients, the numbers that are in front of the formula, we have 2 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So pressure will not affect equilibrium in any way. Now if I decrease the concentration of nitrogen, that's going to make the nitrogen side of our seesaw. Now remember that in our seesaw, the reactants, in this case, nitrogen and oxygen, are on the left side, and the products are on the right side. So if I decrease the concentration on this side, this will cause the seesaw to rise in this direction, just like our picture. So this is the correct answer, but we want to look more at the other ones. So if I increase the concentration of oxygen, again it's a reactant, it's going to cause the seesaw to fall in this direction, which is not the direction we're looking for. And now if I increase temperature, temperature is energy, so energy is a reactant. So again the seesaw falls in this direction and would not cause an increase in our nitrogen monoxide. Question number 7 is simply a definition of equilibrium. And we recall that equilibrium, the rates are equal, the concentrations are constant. Again, question number 8 is another definition. So we know that all solutions at equilibrium are going to be saturated. Saturated means the rate of dissolving is equal to the rate of crystallization. Question number 9 looks for us to increase the rate of the forward reaction, meaning that we're going to favor the forward direction. If we're favoring the forward direction, we are going to be moving towards the right. Remember that if we think of this like a seesaw, we always shift to the up direction. So we want to shift the seesaw so it rises on the right side. Now let's consider our original seesaw. If I increase the concentration of nitrogen monoxide, a product, the seesaw is going to fall in this direction, which is not the direction we're looking for. Now if I increase the concentration of nitrogen, it's going to cause the seesaw to fall in this direction. So this is the best answer. Now if you're unsure of which direction you want the seesaw to fall, simply go and find the results of all of the variables and find the one that's different. So when we look at variable number 4, if I decrease the temperature, notice that the energy is a reactant. So if I decrease the temperature, equilibrium will shift in this direction. And then if I decrease the pressure, remember there'll be no effect because there are 2 moles of gas on the reactant side and 2 moles of gas on the product side. Question number 7 asks us to describe in terms of Le Chatelier's principle why an increase in temperature increases the solubility of potassium nitrate. Again, we want to know why if we increase the temperature, what we're really doing is we're adding more heat. Now, we see that this reaction is endothermic. And because the reaction is endothermic, the forward reaction is endothermic, it will absorb the heat and make more products, dissolved potassium nitrate. So, increasing the temperature shifts equilibrium to the right, thus causing more solubility for the potassium nitrate. Question number 11 asks us to explain in terms of equilibrium. So basically, we just have to describe how saturated is equilibrium. And all we have to do is define a saturated solution. So saturated solutions are in equilibrium because the rate of the forward reaction is equal to the rate of the reverse reaction. Other ways in which you could go and describe why the solution is saturated is because the concentrations of the dissolved and undissolved solute is constant. Question number 12 just has you basically recall a key idea that systems in nature tend to go for lower energy, as losing energy is spontaneous, means it happens without having to put in really any energy. And so lower energy and higher entropy or randomness. So things tend to lose energy and get messy with very little input needed from the surroundings. Just think about your cell phone battery. Your cell phone battery, even if you're not using your cell phone, loses its energy over time. And your room gets messy. If you don't put in energy to keep yourself organized, things will naturally get messier. Question number 13 basically just looks at what are the purposes of potential energy diagrams, and they're basically to show the overall change in energy in a reaction over the course of a chemical reaction. Question number 14 asks us to look for the greatest increase in entropy. Recall that entropy is randomness. When thinking about entropy, do remember to think about the particle diagrams we discussed in the beginning of the year and the descriptions of the various phases of matter. So solids have definite shape and definite volume because their particles vibrate in fixed geometric positions. Their particles never slide past one another. While liquids have definite volume but indefinite shape, as their particles are able to slide past one another, but they still remain in very close proximity to one another. And gases have no volume and no shape. They have no intermolecular forces. They're moving in constant random straight line motion as they completely fill any container. So in this case, gases have the greatest entropy or randomness, and solids have very low entropy or randomness. So in this first equation, we're moving from a solid to a solid and a gas. So we're moving from solid to gas. This is an increase in entropy. In the next equation, we are moving from a solid and a gas. So we have a gas and we're moving to just a solid. So this is a decrease in entropy. Question number 3, we're moving from a gas to a liquid. And again, our entropy is decreasing as we are becoming more organized. And question number 4, we're again moving from a gas to a solid and we're decreasing entropy. So the best answer here is choice 1. The next series of questions, we're asked to look at the potential energy diagram. We're given an equation below. Notice that potential energy diagrams are written in the same left to right orientation as chemical equations. So we begin with the reactants. The reactants are on the left side of the arrow of a chemical equation, and they're on the left side of the graph of a potential energy diagram, while the products are on the right side, and so of the chemical equation, as is the potential energy diagram. So letter B, which is on the right side, is representing the right side of the chemical equation. So this is the chemical formula, or the products. In question number 16, they ask if 682.2 kilojoules is absorbed, how many moles of ethene is produced? So in this case, we're asked for moles and we're given a chemical equation. So this is a stoichiometry problem. This is great review. So when you have a stoichiometry problem, you underline the parts of the equation that you'll be working with. In this case, we're working with our products and we're working with our heat. What we know is we would absorb 682.2, and we'll write that just below the kilojoule value. And we're looking for the moles of ethene. So from here, what we can do is set up a proportion and solve. Notice that I take the coefficient from my chemical formula and place it on the top of my fraction. The tops of my fraction are directly from the chemical equation, and the bottoms of the fraction are directly from the question. Remember, once you set up a proportion, you solve by cross multiplying. When we cross multiply, we'll get that 227.4 times x equals 682.2. And when we divide to solve for x, we'll get x equals 3. So that is our answer, 3 moles. Now, for question number 17, we're asked, how will this potential energy diagram change if a catalyst is added? And recall that catalysts speed up chemical reactions, both the forward and the reverse, by lowering the activation energy. So the activation energy would be lower. Question number 18 has some great vocabulary in it. So the first really great vocabulary word is this term endothermic. Recall that endothermic means heat goes into, or heat is absorbed into, a reaction. While the next really good vocabulary word is this term sublime. Sublime refers to sublimation, which is the change of a particle straight from a solid to a gas. The most commonly understood material to sublime is something like dry ice. Dry ice is called dry ice because it has no liquid phase. It goes straight from solid to gas. And then it asks about the tendency to nature. So basically, you didn't exactly have to know what endothermic and sublime means if you remember the tendency to nature. Recall that things in nature tend to go to lower energy. Things naturally lose energy and they become more random or have higher entropy. So basically, if heat is absorbed, we have a higher energy, not a lower energy. So question 4 doesn't make sense. So here, question choice 2, we're going to a greater energy, but that's not what is represented by nature. And we have a greater entropy, which is represented by nature. Less entropy is not natural. Question number 19 is again reviewing how a catalyst works by lowering activation energy. The next question wanted to know which sample of water has the greatest disorder. When we look at the water, they have different temperatures and different phases. So here we have a gas, two liquids, and a solid. Recall that the greatest disorder would be in the gases that have no definite volume and no definite shape. Now let's move on to the practice question. Question number 1 asks us the role of a catalyst. Recall that catalysts go and they alter the activation energy by providing an alternate pathway. Question number 2, they're giving us a reaction at equilibrium. Basically, they're asking us to define it. And remember that equilibrium is equal rates, constant concentrations. So in this case, choice 3 best defines equilibrium. Question number 3 is showing the dissolving of potassium nitrate. Begins as a solid potassium nitrate, and then it is placed in water where it dissolves. So when it's placed in water, what happens is you'll have the potassium nitrate that is surrounded by water. So the entropy, which is also called the disorder, is increasing. Question number 4, we're looking for the potential energy of the products. Just like chemical reactions, the products are going to be on the left. So in this case, we can see the products are here. So this corresponds with choice D. Question number 5 is looking for the heat of the reaction. Here the reaction is symbolized by delta H. And its formal equation, which you need to know, it's the heat of the products minus the heat of the reactants. Remember, heat is interchangeable with the potential energy. So it's the potential energy of the products minus the potential energy of the reactants, the difference between the two plateaus. The final question for this series asks us which chemical listed on reference table I could represent this equation for the cold pack. Now let's look at this graph. We can see that this graph is increasing. It is an endothermic graph where heat is absorbed. So cold packs work not by adding cold, as there's no such thing as cold in chemistry, but instead they absorb heat. So here, again, we have an endothermic process. Reference table E shows the process of many different chemical reactions, and we essentially need to find one that's endothermic. Here, there's a double asterisk here, and it says a minus sign indicates exothermic. Since we're looking for endothermic, we'll want to find a reaction that has a positive delta H value on reference table I. Also notice in the question it says when mixed with water. So we have to find a chemical equation that involves solutions or solids being mixed with water. So here you can see are all of the reactions that involve a mixing of chemicals with water for the creation of aqueous solutions. And again, recall we're looking for a positive delta H value. So any of these positive reactions could be provided as correct answers. What you could not provide as an answer is any negative value. So potassium nitrate, ammonium chloride, ammonium nitrate, and sodium chloride would all be acceptable answers. Question number 7 is just again defining equilibrium. And remember that equilibrium rates are equal, concentrations are constant. The next question, we're asked to find which of the equations is going to be the fastest. So we have to recall about the different factors that affect chemical reaction. And one of the factors, the major factors, is the nature of chemical reactants. So recall that covalent reactions are much slower than ionic reactions. And solid reactants react slower than liquid and aqueous, which react slower than gaseous. So let's look and see what we have here. So first, let's recall that ionic compounds contain metal and nonmetal. While covalent compounds tend to contain all nonmetals. So let's eliminate the covalent reactions. Reaction 1 is covalent, as carbon and oxygen are both nonmetals. And equation 3 is covalent, as it contains all nonmetals. So now we're left between equations 2 and 4. Notice that equation 2 includes aqueous and liquid substances, while equation 4 includes solids. Aqueous and liquid substances will react faster than solids, so choice 2 is our best choice. Question number 9 asks us again to define equilibrium. Remember, equilibrium have equal rates and constant concentrations. Here we're looking to increase the concentration of A. That means that if we imagine our seesaw, we would like the A side to go up. Now here we can see that this is a exothermic reaction. If I lower the temperature, it's the same thing as removing heat. So our seesaw would fall in this direction. This does not match our target. Now if I add a catalyst, catalysts do not affect the position of equilibrium because catalysts speed up both the forward and the reverse reaction. If I increase the concentration of AB, which is a product, it would cause my seesaw to fall in this direction. So 3 is the answer. Now if I increase the concentration of B, a reactant, my seesaw would fall in this direction. Question number 10 describes what happens to entropy when something dissolves. Well, when something dissolves, it spreads out. It is less organized. Therefore, it decreases entropy. Imagine a sugar cube. A sugar cube, solid, is very easy to carry around. But once the sugar cube is dissolved in a liquid, it is no longer together. It's no longer really easy to carry around all of those particles of sugar. In question number 11, we're asked when a catalyst added, what happens to the activation energy? And of course, we can recall that whenever you add a catalyst, you decrease the activation energy. Question number 12, we're asked to examine entropy when carbon dioxide sublimes. Recall subliming is going straight from a solid to a gas. Carbon dioxide sublimes, it's actually commonly called dry ice. Now the entropy or randomness increases as we move from a solid to a gas. Question number 13 asks to explain how catalysts work. Catalysts, recall, they speed up chemical reactions by providing alternate pathways that decrease the activation energy, or they speed up reactions because they lower the minimum amount of energy required for the reaction to proceed. Question number 14 asks us to draw the potential energy diagram for an endothermic chemical reaction that shows the activation energy, potential energy of the reactants, and the potential energy of the products. Endothermic means heat is absorbed. When heat is absorbed, it is a reaction, a reactant. Okay, so since heat is absorbed, we have to show that the energy of the products is higher than the reactants. because the reactants absorbed heat. Now here, the reactants are from the plateau to 0. The potential energy of the products are from the second plateau to 0. The activation energy is the energy from the plateau to the peak. Question number 15, we're asked to identify the activation energy of the forward reaction. Whenever you see forward reaction, all it means is read the reaction from left to right. If you were asked for the reverse reaction, you would have to read the reaction in reverse or right to left. So here, to find the activation energy as we're moving, again in the forward direction, that's the minimum amount of energy from the starting point, the reactants, to the peak. So here, choice B is our best answer. Question number 16a, we're asked to draw the potential energy diagram for a reaction. When we look at the reaction, we can see that the heat term is written as a product. Recall that the items you put into a chemical reaction are the reactants, and the items you get out are the products. Heat is exiting or coming out of this. So this is an exothermic chemical reaction. So for our reaction, we have to be losing heat or potential energy. So our products will have lower energy than our reactants. Again, here are the products and here are the reactants. Part B asks why the concentration of ammonia decreases as the temperature of the system increases. Well, let's look at what happens to equilibrium. When the temperature increases, our seesaw, which originally is even, is going to have some items added to it on this side. This is going to cause the seesaw to tip, and equilibrium will shift towards the left. So increasing temperature shifts equilibrium to the left, thus decreasing ammonia concentration. This is because increasing temperature favors the reverse reaction. Question number 17 asks us to use Le Chatelier's principle to explain why decreasing the concentration of carbon dioxide would decrease the concentration of carbonic acid. So recall that again at equilibrium we start with a balanced system. But if I decrease the concentration of carbon dioxide, a product, then my system is going to shift in this direction. If I decrease the carbon dioxide, there'll be less collisions of carbon dioxide with water to produce acid. Again, if I decrease this, it'll collide less often, making less reactant. In addition, decreasing shifts my equilibrium to the right, thus producing less carbonic acid. Question number 18, we're given an equation where we have the reactants and the products, and we're asked to identify the correct potential energy diagram. Notice energy is here, and it is a product, meaning that this is an exothermic reaction. So here we're looking for a reaction that's losing energy. Now, choice numbers 3 and 4 have no activation energy and are just odd looking. So those cannot be the choice. If we're looking for the energy to decrease, choice 1 is the best choice. Notice that choice 2 is increasing.